Okay, so probably there's still somebody missing, but I mean, not that much time. It's a busy afternoon. So, Matt, the last lecture, sadly, I have to say, it was very nice. So, please.
Okay, thank you very much. Yeah, it has been a hell of a week, and we're going to try and wrap things up as best we can in the hour that we have. I realized that there's no way that I can finish the storyline I wanted to share with you guys completely on the blackboard. But at the same time, I'm really happy with the foundation we put together, because now I think you'll have some basis for when I start to tab through the slides and point things out sort of a more high level. The danger, of course, of the PowerPoint talk is that I get super excited and just keep going. Please continue to stop me, interrupt me with questions. That's still okay, just like before. Okay, so last time we did a couple of calculations. The second calculation that we did was the radiative process, quark-quark goes to quark-quark, plus a small x gluon. X here meaning the momentum fraction k plus over p plus, so that this gluon is radiated at mid-rapidity and not in the beam fragmentation regions of either the projectile or the target. Light front coordinates were a really helpful tool to do that. We found something really interesting, which was that in kinematics, the high energy scattering, that there was a very delicate cancellation of initial state and final state radiation, that essentially kinematically the two processes were identical at the amplitude level. They produce radiation that sits directly on top of each other, and they differ by a minus sign, that minus sign coming because the propagator in one case was space-like, in the other case it was time-like, and that was the difference between initial and final state radiation. That resulted in 0, so that QED at high energies is boring. You have no photon radiation if you don't shape the electron to accelerate it. But quarks, on the other hand, are free to radiate even if they don't accelerate kinematically because they're non-abelian particles. They interact by rotating in color space even if they don't reflect and scatter. And that's why the high energy kinematics is uniquely sensitive to the non-abelian nature of QCD. And sort of we ended on this teaser that we've set up now a competition between the smallness of the coupling constant in QCD and weak coupling and the largeness of a phase space logarithm. Here, this log of the center of mass energy is just the total rapidity interval. That if you have a soft gluon being radiated, you essentially radiate gluons uniformly across mid-rapidity. So now I want to walk through what are the implications of this and why do we talk about X? Because the entire discussion yesterday was about high energy QCD and had very little to do with X. So let me start off by taking a bit of a detour to give you an introduction to deep inelastic scattering. I'm sure many other people here already and later on in the week will, or next week will tell you more about this. But this is my high-level overview. Whenever I talk about deep inelastic scattering, I always like to make the analogy between what we understand about the structure of the proton and what we understand about the structure of the atom. The proton, like the atom, of course, is not a fundamental particle of nature. It's a bound state made up of quarks. And the structure of the proton comes from the nature of the QCD interactions. So in exactly the same way that QED generates all of atomic structure, all of chemistry, and we learn something about QED by studying in detail the fine structure, the hyperfine structure of the hydrogen atom. If we want to learn about QCD, one of the best ways we have to do it is by studying the structure of the proton. It's no accident that the proton and the hydrogen atom were both discovered simultaneously about a century ago. Once we finally had high enough energies to start peering inside materials, the Rutherford gold foil experiment, of course, famously looked for high Q² scattering, high recoil particles. And just like in deep inelastic scattering, that high Q² back scattering is the signature that you interacted with something point-like at short distances. In the century since we have discovered the proton and the atom has grown up, right? So our understanding of QED, our ability to predict the structure of the atom, is at an astronomical level of precision. This is just a random paper that I pulled that I found at one point. Blows my mind. A calculation to 4 loop Feynman diagrams, 891 of them to 1100 digits of precision for the anomalous magnetic moment of the electron. Like, this is incredible. Like, one of the greatest triumphs of theoretical physics ever. Our understanding of QED is so precise, we literally use it as the definition of time itself. We understand the hyperfine slitting of cesium so well that that is now the most accurate definition of the second according to the National Institute of Standards and Technology. And in contrast, we understand QED so well that the theory has reached maturity, but the proton still is a moody teenager saying you will never understand it. And we do not even understand where basic properties of the proton emerge from its fundamental constituents. The proton spin puzzle, the proton radius puzzle, the proton mass puzzle. This is the one that I was referring to, where if you can suddenly solve from the QCD Lagrangian how protons and neutrons fall out, you instantly win $1 million because it's one of the millennium problems. I showed you these slides before. The fundamental difference between QED and QCD is one tiny change in the gauge structure of the theory. The fundamental ingredients look like Maxwell's equations, particles and fields, but in QED you have only one kind of charge. But in QCD, the non-abelian nature, the fact that you have multiple independent directions, directly leads to self-interactions of gluons. The self-interactions of gluons directly lead to confinement. I don't think this plot has been shown yet at the school. This is the heavy quark potential, very famously. This is the gluon-mediated interaction potential between two quarks that are so heavy that they're fixed in place. This is an early lattice calculation. You see very nicely the attractive 1/r Coulomb potential at short distances where asymptotic freedom works. And you see it transitions to a linear potential instead of flattening out to 0 like the Coulomb potential does. The linear potential is of the form sigma times r. Sigma has units of force, and sigma is called the string tension. It has a numerical value of about 1 ton. So that's the statement. If you try to rip two quarks apart, you have 1 ton of force between them that never gets smaller. And of course, that means you can't just ionize a quark out of the proton if you want to measure proton structure. It's not that easy as we would use to measure atomic structure. So in exactly the same way, you cannot take a bar magnet and break it apart and find an isolated north and south pole. You cannot break apart a hadron into its constituents. You end up with smaller bar magnets that have the same properties as before. So we have to work a lot harder to study the structure of QCD compared to QED. And we see the differences between the theory of QED and QCD directly in our particle detectors. This is an event display from on the left. It's supposed to show electron-positron come in along the beam axis. Here they've collided and they make exactly one absolutely beautiful muon pair, mu plus, mu minus. So it's exactly 2 to 2, gorgeous. But then you do proton-proton scattering and there's a whole bunch of stuff that comes out. QCD is messy because of confinement. So where does a particle accelerator come in? You want to measure proton structure. You want to learn what's inside the proton. Normally, we talk about a microscope. A microscope, as we normally think of it, is an optical microscope, which is, of course, limited by the wavelengths of visible light. Visible light is a few hundred nanometers at most in the deep UV. And so that's a minimum energy of, say, 2 eV for your measurement. Something more powerful than the optical microscope is an electron scanning microscope, which is just a tiny particle accelerator. It's a thermally generated beam of electrons where you measure the scattering of the electrons and reconstruct images of things much smaller than that optical limit. So it's really not a big conceptual jump at all to go from scanning electron microscope to electron-ion collider. It's exactly the same principle of using the scattering of the electrons to reconstruct images, but now there is no maximum energy in theory. It's whatever you can put together into your particle accelerator. The most root S you can get gives you the most resolution of proton structure. So deep inelastic scattering began with the SLAC MIT experiment in 1968. This is what helped us discover QCD in the first place. I will walk through some of the logic that led us there. The current apex of deep inelastic scattering in terms of energy is Hera. Hera was the highest energy and the only proton-electron collider thus far. It ran until 2007 at a center of mass energy of 318 GeV. And of course, we're looking towards the future for the electron-ion collider, which doesn't have quite as high of energy as Hera, but has a lot more flexibility in terms of polarization control, ion species, as well as much higher luminosity. Okay, theory of deep inelastic scattering. Now I finally will have the ingredients to tell you what X is. We've talked a lot about how gauge bosons interact with each other. They always interact by coupling to some kind of conserved current. And in the case of QED, that's the electromagnetic current that we studied before. So if I have inclusive electron-proton scattering, my observable is electron plus proton goes to scattered electron plus anything else. Could be a proton, could be a bazillion particles. They all get counted the same way in my observable. The basic process as a Feynman diagram looks like this. I've got electron and proton coming in. The electron interacts by QED. I know exactly how that behaves. The electron radiates a photon. The photon does something in the proton. And then the proton maybe comes out intact, maybe it blows up. Whatever it does, that's described by the interaction of the photon with the proton. And so here's an example of an event display from Hera. You see very cleanly the two sectors shown there. Electron comes in, proton comes in, you see the backscattered electron. That by itself is enough to allow you to totally reconstruct the kinematics of what did you throw at the proton from that photon and what came out. And you also see the spray of hadrons that comes out when you shatter the proton. The beauty of inclusive deep inelastic scattering is you don't have to touch that at all. If you do, you get more information, but the theory becomes much more complicated if you want to disentangle transverse momentum dependent parton distribution functions. But if all you need is a one-dimensional picture of proton structure, it's sufficient to just reconstruct the scattered electron, which is much cleaner. So we talked at a theory level before about the coupling of the photon to the conserved currents. I can say in general, even if I don't know anything about QCD, that the nature of that interaction comes in the form of photon that was delivered from the electron and some matrix element of the electromagnetic current. If I had no idea what QCD was, I could still write down a matrix element of this form. So that's my scattering amplitude. Now I know I have to square the scattering amplitude and integrate over some phase space to get the cross section. The amplitude squared now looks like this. Now I've just dropped the electron because the QED part of this process is really simple. That's so simple, I can write it down in one line, calculate it all out, and it's known. This is an uninteresting part of the process. Really, for me, the electrons are just a source of photons. And the details about energy that didn't come through the photon is just kind of an inefficiency for me. So I don't really care very much about inelasticity Y and things like that. Those are just losses that didn't actually contribute to scattering on the proton. The relevant part of the process is just the scattering of the virtual photon on the proton itself. Question? Yes, ma'am.
It looks like the vertex is included in the Electron term. That's true, or am I mistaken?
Maybe you mean the factors of the electron charge. So those have been factored out, yes, and they've been pulled out up front by convention. The vertex is still there in the form of the gamma mu coupling. Is that what you're referring to? Yeah, so I mean, the vertex is still there, but you're right that in convention they've factored out the coupling constants and they've just gone in front. So the relevant part for studying QCD is this piece, the hadronic tensor. We said at the amplitude level, I get a matrix element of, I started in the proton, I hit it with a current, and then I have X, anything in the final state. Well, if I sum over X, I have a complete set of states. So it makes perfect sense that the amplitude squared, after I remove that complete set of states, X in between, is a correlation function of two electromagnetic currents. You can think of it really as if this was a forward amplitude saying, this photon excites a quark inside the proton, and then it de-excites by radiating that photon. It's a little bit of a fictitious analogy as if this was a forward scattering process, but it's literally true in the sense of the optical theory. So I wanted to motivate, what are you learning? What is this matrix element? Without knowing anything about QCD, we know that deep inelastic scattering tells us about electromagnetic correlations inside the proton. As far as what kind of structures this can take, well, that's strongly constrained by Lorentz invariance. This process, after I've taken away the electron, only depends on two variables, P and Q. It's just the proton and the photon you're hitting with. So I have a tensor valued function, W mu. It's got two indices running around. It's a function of two momenta, P mu and Q mu. There's only a few ways that I can combine P and Q to get two indices upstairs. Everything else has to be an unknown function of invariance. And there's only a few invariants that I can construct. So the natural thing is, if I don't know anything about this function, at least let me decompose it in terms of unknown scalar functions called structure functions. Yes, ma'am.
So in the hadron tensor, the only place that we see the interaction with the virtual photon is in the e to the iq.x term, is that right?
The interaction with the virtual photon is the coupling to the electromagnetic current here. So the vertex was J mu, A mu from minimal coupling. Here's the J mu. The A mu went into the propagator, and that now is the 1 over q to the fourth. So before we knew anything about QCD, we could have already said this much. So now I can finally define what X is. The relevant QCD part of the hadronic tensor depends on two invariants. It depends on P and Q, and I can make two scalar invariants from those momenta. I can take the photon momentum Q and square it, Q is a space-like momentum. So if I take the 4 vector Q and square it, I get a negative number. Conventionally, we just take the absolute value of it, and we call that capital Q squared. In terms of scattering kinematics, this is directly related to the energies and the scattering angle of the electron. So you see, the larger the scattering energy, the larger the Q squared, the larger the recoil angle, the larger the Q squared. Q squared, since it's a space-like variable, you can always go to a frame where Q squared is a transverse momentum scale. So that means Q squared is effectively a transverse resolution. If Q is a transverse momentum, then 1 over Q is the transverse position resolution information. So that's sort of the standard intuition we have for what DIS is telling us, that Q squared tells you whether you have deep inelastic scattering or like regular elastic scattering. If Q squared gets very large, then you're actually looking inside the proton. If Q squared is much larger than the mass scale of the proton, so much larger than 1 GeV, then the length scale that you're measuring the proton over is smaller than the proton itself. So if I do deep inelastic scattering, I see a hard scattering event just like Rutherford scattering, and I say, oh, my Q squared was 5 GeV squared. And then I know for sure that I hit something charged, some electromagnetic constituent inside the proton. So the story about Q squared is pretty well known. The story about X is much less so. X is another independent variable that you can make. If Q squared is a transverse variable, X is a longitudinal variable. X is something that involves a comparison of P with Q. So you can define various combinations. The scale nu is a similar scale, but X is the one that has sort of stuck around. You can again relate this to the transverse momentum divided by the energy transfer in the rest frame. That's all well and good, but what does it mean? The simplest interpretation that I know of for Bjorken X is in terms of a time scale known as the Yawfin time. If I go to the rest frame of the proton, then this time scale, 1 over m times x, is the time scale of the interaction of the virtual photon. You can already see that here at the level of the definition of the hadronic tensor. So Bjorken X enters one of the components of Q. And that component of Q tells you about how separated these two currents are. It's related to the Fourier transform. So it's literally a case of this point and this point are separated along a light-like direction by the Yawfin time. And as X gets smaller, those two vertices start moving further and further apart. If X is a number of order 1, then these two things are sort of inside the proton. And you have a simple picture that looks like my photon hit a quark that was already inside the proton, puts it back in, and that's how I get a number operator measurement inside the proton. But things start to get weird when X gets small. When X gets small, that resolution time gets longer and longer. And that means that you're able to resolve shorter and shorter lifetime quantum fluctuations. So one way of thinking about it is it's a boost factor. As you go to higher and higher energies, lower and lower X, you increase the time dilation effect on quantum fluctuations. So you're able to resolve things that used to look like just 3 valence quarks in the proton. Now at smaller X, you can see, oh, it was valence quarks and soft gluons. And if you keep dialing down X, now you see more and more of those quantum fluctuations. So in this analogy, the deep inelastic scattering is a camera or a microscope. I would say Q squared is your resolution. That's the number of pixels you have. X is related to your exposure time or your shutter speed. That's how fast you're able to take the picture and what particles you're able to see based on how long they live. Question?
Yeah, could. Yeah, can you go back to the last slide?
Sure.
Okay, so you've kind of like taken the two diagrams.
Yep.
But that's not like really what's happening, really, like some other final state is coming out, like either Proton or some
Right,
other
so this is at the level of the amplitude squared. So this is a Feynman diagram, if you like, for the cross section, coming from squaring the particular diagram. Yes.
So could you look at the Yawfin time as like the time that it takes the, internal quarks to rehydrogenate?
I'm not sure about that. The thing that I know for sure is coming from this Fourier transform. So I know the Yawfin time having a simple interpretation at the level of the amplitude squared. I don't know if I could give a simple interpretation at the level of a single amplitude. Sorry. Okay, so that is what X and Q squared are. This is what we saw when we got our first peek inside the proton. So these are actual plots from the Nobel lectures from Friedman, Kendall, and Taylor, who were on the SLAC MIT experiment. Without knowing anything about QCD, if I just take that hadronic tensor and I decompose it into all allowed structure functions, there could be two called F1 and F2. And a priori, both F1 and F2 could depend on both of the kinematic invariants, X and Q squared. So when they actually did the SLAC MIT experiment, they found two critical pieces of information that in fact you don't have as many independent variables as it looks like. For one thing, F1 and F2 are not independent, they're related to each other. The ratio of F1 to F2 is this fixed proportionality as soon as Q squared starts to get bigger than about 1 GeV squared. The particular value that they converge to here is exactly the value that you expect if whatever the electromagnetic constituents of the proton are spin 1/2 fermions. This is referred to as the Kalin-Gross relation. And that's part of how we know that quarks are real. We see that inside the proton, you are hitting something which is a spin 1/2 point-like charged particle, which just so happens to be what we expected in the form of quarks. If there were different spins, like if they were scalar constituents inside the proton instead of fermions, then you would still have a relation between F1 and F2, but it wouldn't be this relation, it would be a different relation. So this particular form of the Kalin-Gross relation gives us evidence that quarks exist as spin 1/2 fermions. The other thing is that not only are F1 and F2 not independent, they don't depend on both kinematic variables. They could depend on both X and Q squared, but at least at the kinematic reach that they had at SLAC MIT, they only depend on X. They are independent of Q squared. And this is the phenomenon of Jorgen scaling. If I take this literally, if Q squared is my resolution scale, and it doesn't depend on the resolution scale, that's weird. It looks like the quarks are point-like at every resolution. As soon as I see inside the proton, I see point-like particles, and I can zoom in as much as I want, and they're still point-like. That's okay unless you know something about quantum field theory. And quantum field theory says that should not happen. That's exactly the opposite of what happens in QED, as we've discussed. Fluctuations are allowed to blow up to infinity at short distances. So why is it that it is point-like at all scales? If I zoom in, I should see more and more quantum fluctuations going crazy, but we don't. And if quantum fluctuations are allowed to blow up, but they don't, the only explanation is the probability of those quantum fluctuations is going to 0 at short distances. And that means asymptotic freedom. So the observation of Jorgen scaling demands a theory which has asymptotic freedom to explain why it is point-like at all scales. And this is what led us directly to QCD. Once you know I need something with 3 different color states to describe the omega minus baryon. Oh yeah, free quarks don't happen to show up in my detector. Things are point-like at all scales. The one piece that brings it all together is an asymptotically free theory. And as soon as you know number of colors is 3, that pretty much uniquely gives you QCD. So that was our first picture of what's inside the proton. This is a modern picture of what's inside the proton. This is an extraction of the Parton distribution functions, number densities of quarks and gluons inside the proton as extracted from Hera, here shown as a function of X. This is probably familiar to everyone, but let me point out a couple of important features here. There are 2 very different regimes of proton structure. The one that lives at large X is the one that we normally think about when we think of the proton. Our naive picture of the proton is it's made of 3 quarks, 2 up quarks and a down quark. And you know, that's literally true to a certain extent. In the region where X is large, there are predominantly up quarks and down quarks. There are about twice as many up quarks as down quarks. And if X is a momentum fraction, then if all 3 quarks were just sitting statically at rest inside the proton, then they should all share an equal fraction 1/3 of the proton momentum. And yeah, you know, the peak of these guys is pretty close to 1/3. So this picture of the valence proton is true in a certain region, but it is not the whole story. That valence picture of the proton, if you look at the position of the peaks, it's actually downshifted slightly from 1/3. That's because QCD is a dynamical theory. And even if you start off with 3 quarks happily sitting at rest, they're going to start interacting and radiating gluons. And all of the radiation that comes off of that is going to bleed energy down and take energy away from those valence quarks. So what you see is 2 different distributions, the valence structure of the proton and the radiative structure of the proton. As we've seen, QCD loves to radiate gluons, even quarks that have low momentum fractions. So this radiation distribution has a high density of gluons, also C quarks, each of which has a very tiny percentage of the proton momentum. So you have 2 up quarks and a down quark that carry, I don't know, 20% of the proton's momentum each, and the rest is in a cloud of radiation. This tells me that depending on where I look at the proton, I could see 2 very qualitatively different pictures. The proton at large X is a dilute system, where I can have this picture of one quark gets knocked out, I have coherent color lensing that pulls me back towards the other quarks, and maybe that's my explanation for the Sievert's function. But that explanation doesn't make any sense in the dense proton, where I've got billions and billions of gluons, and the color interactions are much more complicated. So I wanted to emphasize here that already at the level of deep inelastic scattering with a focus on Q squared, we see that something weird is happening at small x. If I take the agnostic approach that says, I don't care about small x, everything is D-lab, everything is Q squared. You can get a lot of mileage out of that. You can extract the PDFs. You see the structure functions are starting to blow up, but you can still fit them with D-lab. But if you really dive into the fits, you see that something systematic is happening at small x. This is an NNLO fit based on D-lab only. And you see that the chi-squared of the fit, the quality of the description, systematically degrades as you include more and more small x data. This is telling you that just the D-lab fit, something that ignores small x physics by itself, starts to have problems describing the data. The data requires something new coming from the small x region. And the thing that it requires is leading log x resummation. This is exactly Fkl, which we talked about last time. So if you start to include these large logarithmic effects, you stabilize the chi-squared. Now, this is far from a smoking gun, I would say, but I'm happy that there's clear evidence I can point to from DIS itself that says you cannot describe everything with D-lab even if you try. You have to have something else from small x. So what is the something new in small x? The picture of DIS at large x is usually drawn as a handbag diagram. I would call this a knockout process, where your idea is, I have some quarks inside the proton, and I hit one of them really, really hard with a photon, and that quark goes flying out. That's fine. That's perfectly good for kinematics where x is largish. Let me go back to that picture here. And I'm interacting over a distance that's inside the proton, right? Like, I have to hit it where there are quarks to kick out. Now, when you go to small x, however, something gets weird about those kinematics, right? The distance between electromagnetic current number 1 and current number 2 starts to get much larger than a fermi. And then that interpretation of, I just knocked a quark out of the proton doesn't make a lot of sense anymore. You're interacting over much longer time scales than the size of the proton itself. The solution to this conundrum is that the electromagnetic current can do more than just knock out a quark. It can also cause pair production. So I can have photons that are very, very far away from the proton itself that interact electromagnetically far in the past or far in the future. That electromagnetic interaction of the photon can create a quark-anti-quark dipole. And then the thing that hits the proton is not a photon at all. It's a baby proton-proton collision. It's a tiny hadronic system made up of quarks, which is overall color neutral, that is then scattering on the proton. So DIS at small x changes radically. It no longer looks like a handbag diagram, a knockout process. This one is technically an NLO process, right? It's got an extra vertex in it to let you fluctuate and then scatter. But paying an extra price of alpha s is no big deal compared to running out of quarks. This expression is power suppressed at small x. This expression is only suppressed by 1 factor of alpha s. So at small x, you change the leading behavior of DIX. You change it from being handbag knockout kinematics to small x coherent dipole scattering kinematics. So when you do that, you turn DIS, you turn photon-proton scattering into something that looks like a hadronic collision. It looks like quark-quark scattering, which we just calculated. The relevant degrees of freedom are now highly boosted, highly Lorentz contracted. Right, so these guys have long lifetimes. The phase of the dipole that's propagating through the quark, propagating through the proton field, isn't really changing very much during this very small interaction time. So what you have is essentially a coherent phase, a coherent line integral. This could include one gluon exchange. This exponential, if you expand it back out, is just one vertex IgA plus, exactly the Eichenal vertex that we used when we calculated quark scattering. But the exponential allows you to have many of them, not just one gluon, but two gluons, n number of Eichenal gluon exchanges. Yes, sir.
So the photon forms a Q bar pair,
Yes.
but then you're calling that a proton?
I'm making the analogy that this now is a hadronic collision mediated by gluon scattering, exactly as when we did quark scattering yesterday. That's very different from something like this, where you have T-channel quark exchange. Here you have the quarks are coming in the S channel from minus to plus infinity, and the dominant dynamics is gluon exchange. Exactly as before.
It's an asymmetric collision, right? Why you calling
Yes.
the Q bar to be proton? Shouldn't it be some other like mesonic pattern?
Yeah, it's not literally a proton. I'm making a metaphor to say that this is something smaller than the proton. Maybe this would get some traction then. There's a big story of small systems in heavy ion collisions. We say, oh my God, I'm making the quark gluon plasma not only in gold-gold collisions, but also in deuteron-gold collisions, maybe even proton-proton collisions. When does it turn off if I go to small systems? Well, you don't have a smaller system than the proton. Maybe the pion if you work really hard. This is a system which is a smaller system than the proton. So the electron-ion collider is the vehicle for doing small system scans that allow us to continue the question of when the QGP turns off. This is a small hadronic system of arbitrary size. And in fact, I can select on whatever size I want because the size of the dipole is controlled by Q. So I can go to the EIC and say, I want a system smaller than a proton. Do I still have collective flow or not? And just by bidding in Q squared, I can dial on these quantum fluctuations. So the point is that the modality changes. It goes from being quark knockout to gluon scattering, exactly as dominates proton-proton collisions, exactly as dominates heavy ion collisions. Yes, ma'am? Sure.
When you say large X, do you still mean less than one?
Yes. So the things that I call large X are probably quite different from what most people at JLab call large X. When I say large X, I mean X of order 1. Large X to me is something of order 1. So I'm thinking things like X is a half or X is a third, things that live in the valence region. I do not necessarily mean that X is asymptotically close to 1. That's the more stringent condition that 1 minus X is a small number. This I'm not talking about, this I am. And second?
So the small X with the quark antiquark, can you look at that as pion? Or is that a
Pion has a certain set of quantum numbers. This is a vector particle, so to speak, because it comes from a fluctuation of the virtual photon. Maybe a good example is if I make an exclusive process instead of an inclusive one, I can say, what's the probability for that photon to come in and maybe a J psi to come out? Then you really are selecting on photon creates a charm-anti-charm pair, and then the charm-anti-charm pair coalesces into a J psi device. So it's some kind of vector meson. It doesn't necessarily interact with itself long enough to actually form a meson, but it has some probability of doing so. Okay, other questions? Yes, sir.
Yeah. So you said at the beginning that the advantage of having EIC is that it's a clean environment.
Yep.
But now you're telling me that with a photon, you're creating actually hadron, virtual hadron.
Yep.
So it's not so clean anymore.
But still a lot cleaner than if you had proton-proton collisions or ions, all that stuff. Yeah.
Okay.
And I'd say most importantly, the QED type interactions are factorizable and controllable here. There are actual factorization theorems that continue to hold even at small x, which we just don't have the advantage of for PP and heavy ions. Okay. There's a lot of hand waving that gets passed off as science in hadronic scattering, and you can't cheat like that when it's EA collisions or ED collisions. So the main point here is that there is something fundamentally different about DIS at large X and at small x. It literally changes the scattering modality, and the relevant degrees of freedom change. The relevant degrees of freedom for this kind of scattering are Wilson lines. Eichenal high energy quarks, antiquarks, gluons, but something whose root S is going to infinity, and that who rams through a background field of gluons. Depending on how many gluons you have there, maybe you can just truncate the expansion and maybe only single scattering matters. Or maybe you have to include double scattering. Or maybe these are non-perturbative gluons, and you have no ability to truncate the series at all. then you just have to stick with the line integral, whatever it may be, and you have no ability to do the expansion. So this is the natural language, the natural variables that one uses to describe DIS at small x, or any process at small x for that matter, since DIS at small x is exactly the same as proton-proton at small x. So the relevant variables are everything that you can build out of Wilson lines. The simplest object that I can make out of Wilson lines is a single dipole trace. So if I look at this amplitude squared, I have the photon, it creates a quark that has some color flow, goes through into the complex conjugate amplitude where it's removed. The anti-quark flows back the other way. This is a closed loop of color flow. That closed loop of color flow is nicely gauge invariant, so you can calculate it in whatever setup you want. And the relevant degree of freedom is this dipole scattering amplitude. So this is literally the S matrix for the interaction of a quark-anti-quark dipole in a background of the gluon potential of whatever your target is. So when we start talking about DIS at small x, or any process at small x, it's dipoles, dipoles, dipoles all day long. So I hope this is starting to look familiar. We worked very hard to construct the elastic scattering baseline of quark-quark scattering. This is just the leading part of the Wilson line. This is the single gluon exchange, which is the first non-trivial part. If you now staple on two gluon exchange, which is eigenal, it's not really much more complicated than one. And if you resum all n of them, you get exactly the Wilson line of the previous slide. And we saw that once you have Wilson lines, eigenal scattering, this is not the whole story. Radiative corrections can change the energy dependence because they start to introduce large logarithms coming from the huge rapidity available to radiate soft gluons. So the next natural step is, if I know I need to build DIS out of Wilson lines, then I need to start calculating small x radiative corrections to the Wilson lines that are going to generate more and more complicated operators. Yes, ma'am?
What's the Wilson line?
The Wilson line is this. This is the path-ordered exponential. So think of it like a WKB approximation. So it's a semi-classical description. You say, I've got a particle at point x, it goes to point y, and it goes through some background field. So the Wilson line, another way to say it is, this is literally the propagator of a quark moving through a background field. So a Wilson line is V of x perp equals, I have a quark which is going through, it's at transverse position x perp, and it undergoes one gluon exchange with an external potential A plus, another gluon exchange with an external potential A plus, any number of those. So the Wilson line doesn't, I don't have to say what A is. Whatever A is depends on what the target is. But I know that a high energy quark interacts with that background field in a very simple way because eigenal kinematics are really simple. Wilson lines, by the way, are also the correct description for high energy particles like jets. If you want to describe a jet going through the quark gluon plasma, you do it exactly this way. It's a high energy jet which interacts potentially many times with the background field, whatever that background field might be. Other questions so far? Okay. So if the DIS cross-section changes qualitatively when you go to small x, so do the PDFs. The PDFs and the cross-section are related one-to-one by collinear factorization. So if I know this cross-section changes from knockout DIS to dipole DIS, well, I guess my description of the PDF itself is also changing from being something that looks like psi bar gamma psi knockout process that looks like this to sort of an operator that looks like this. All right, a little bit of notation here. The thick blue bar represents the gluon field of the target. Essentially, in the high energy kinematics, all of these gluons are Lorentz contracted down so that they're a delta function in position space. They have zero width because everything's infinitely Lorentz contracted. So, that's what the blue shockwave is supposed to represent. That's where it hits the proton, that's where you go through the background fields. And if I now calculate all possible time orderings, I could have had, right, so the cross here is where the quark operator is. This is where the electromagnetic current is. So this is literally, photon comes in, maybe the photon goes past and interacts over here and it pair produces there. Maybe it pair produces before, and then I have actual quark-anti-quark scattering of the proton. And in general, I have all four combinations. It's a little bit weird, right? This is a non-interacting term. This is not a contribution to the T matrix. It's a contribution to the S matrix. But when I add up all of the contributions, that exactly cancels the non-interacting part of the Wilson lines. If I replace these guys by 1, I get 0 as I should. So summing over all of the time orderings gives me an expression for the PDFs in terms of dipole amplitudes. And the other piece that connects them is the photon wave function, the actual probability which one calculates in QED. The actual probability of the photon to fluctuate into a quark-antiquark pair. That's textbook material that you can calculate directly from the QED vertex. So then I can construct an expression for the PDFs in terms of an integral over the phase space of the quark-antiquark dipole coming in. This is sort of an extra loop that I have to suffer through. It's a little bit annoying that there's an extra loop already at tree level before I get to the interesting dipole scattering physics, but so be it. The operator now that controls the energy dependence or the X dependence of the PDF are completely encoded in these dipole traces. So the problem has now been reduced down to calculate the scattering, the energy dependence of a quark-antiquark dipole interacting with the target, whether that target is a proton, a nucleus, something else. Any questions so far? All right, so let's set up the calculation to get those radiative corrections. We need something which is our initial condition before I start calculating radiation. The initial condition doesn't really matter that much. We can take it to be something simple. I could take it to be, for example, quark-quark scattering. I still have to have a dipole. I have my photon coming in, so I have a quark and an antiquark, but I can pretend my target is as simple as I want, just to have an initial condition for the evolution. So I can literally take the answer that we had on the board yesterday for quark-quark scattering, add in antiquark-quark scattering, and the sum of those two things has this form. Notice that it is energy independent, exactly as we calculated yesterday. It has some transverse dependence. Here it's all very natural to write it in transverse position space, not transverse momentum space, but they're just a Fourier transform away from each other. So you have some transverse momentum dependence, energy independent in the initial condition, just like we had before. Now the exercise is to calculate radiative corrections. So in this picture, I have Wilson lines. I've got a quark Wilson line, an anti-quark Wilson line, and what I can have is soft gluon radiation at a new transverse position x2. And that extra gluon that's getting radiated could pass through the shock wave and contribute to the scattering, or it could be a virtual correction, which it gets emitted and absorbed before or after. So my radiative corrections come in two types, real and virtual. The real correction, since the gluon passes through the shock wave, that means it was emitted before you hit the proton and it was absorbed after you hit the proton. Those change the operator. Before I had a Wilson line at position 0 for the quark, a Wilson line at position 1 for the anti-quark. Now I have QED vertex with color A, QED vertex or QCD vertex with color B, and now a Wilson line for the gluon. The gluon now also passes through the background field. You have a similar expression for the Wilson line of the gluon, but in the adjoint representation instead of the fundamental. So the main point here is when you have radiative corrections, if that extra radiated parton also scatters, well, I guess you got a more complicated operator out of it. If it doesn't scatter, you're lucky, and then instead you just get the same operator back. I started off with an equation for a dipole. The virtual correction is still a dipole. The real correction is something worse. So these are radiative corrections specifically where I've radiated and absorbed the gluon from this line number 1, particle number 1. Yes, ma'am.
Is it accurate to say that radiative corrections are photons for your electron, but gluons for your quark?
Yes, I think the big thing one worries about on the electron side are 2 photon exchange contributions. So in general, you could have radiation either off of the anti-quark line or radiation off the quark line, or you could have a mixture where the gluon is radiated off of one of them and absorbed by the other one. It's fairly simple when the radiation is coming from one particle and absorbed by the same particle. You might call these ladder emissions, because if I start chaining those things together, it looks like I had a quark and then I had a soft gluon, and then I had a soft gluon, and then I had a soft gluon. And you build a ladder out of these structures. The ones that are emitted by one particle and absorbed by another particle don't have that simple ladder type topology to them, but they're still trying. So the ingredients for this just come from the wave function literally the light front wave function, just like we talked about before, for the quark to split into a quark-gluon system. In momentum space, that dependence is 1 over k perp squared. And if you Fourier transform it, it's just 1 over x perp squared. So this factor in red here is just the spatial part of the wave function. This first term, 1 over x21, x21 is the distance between position x2 and position x1. So that x21 is that distance, and that distance is exactly the wave function of this splitting. So this term is exactly the term where the gluon is radiated off of particle 1, and it has the new position number 2. Likewise, if I radiate it off particle 0, then I get something sensitive to the distance x20. But it's the same distance in both cases. For the more complicated non-ladder type emissions, I could emit it off of particle 1, so I have one factor of x21, and I could absorb it on particle 0, so I've got one factor of x20. So these are all of my building blocks. When you stare at those ladder emissions, one thing starts to pop up that looks a little bit concerning. We said that these things have a transverse momentum or a transverse position dependence of the form 1 over x squared. Well, if I'm integrating d2x over x squared, that's logarithmic. Does that generate yet another logarithm that I've got to worry about? The logarithm that we talked before was a longitudinal logarithm, a rapidity logarithm, which came from that longitudinal momentum dependence. So if there is an extra transverse logarithm here, that's weird, and that changes the power counting. But a miracle happens. That miracle is color transparency. The region where this thing starts to become logarithmic is when that distance x21 goes to 0. But if x21 goes to 0, then this is a teeny tiny fluctuation. And that gluon is sitting practically right on top of the quark that birthed it. And because of color transparency, for this case, when that gluon passes the shock wave, that tiny extra fluctuation that you added doesn't really interact at all. Because of that, there's no difference between the virtual correction and the real correction. And these guys cancel each other on the basis of color transparency. So even though it looks like, hey, that transverse integral is trying to become logarithmic, actually it doesn't, because the rest of the integrand goes to 0. You can see that clearly from the expression here. If I take the position number 2 and I put it equal to the position number 1, then I would have V1 dagger, that cancels, and then I just get 1. And then I would have trace V0, V1 dagger minus trace V0, 1 dagger, which is 0. This is the physics of color transparency, that if you have a tiny fluctuation, it hardly interacts at all, and therefore it cancels against the real and the virtual corrections cancel each other. I'm belaboring this point now because this transverse logarithm is exactly the one that comes back for the case of polarized evolution equations. And there it is not benign. There color transparency does not save you. And you do in fact get doubly logarithmic evolution equations, which are significantly more interesting than what I'm sharing with you now. Okay, so what does the final beast look like? Yes, sir.
Why do we call that color transparency? This is only a question about the terminology.
Sure. It's transparency in the sense that that the medium is optically transparent to the system. That you have whatever the shock wave is going through, and that this tiny probe has S matrix going to 1, I guess. So I think it's transparent in the sense of like optical thickness. I don't know if that helps or it's just a nomenclature thing. Thank you. Sure. Okay, so this is the whole result. There's this very nice relation that if I take both of these pieces, the ladder and the non-ladders, when I add them all up, they form a beautiful perfect square. I've got 1 over x21 squared, 1 over x20 squared, and a cross term with a factor of 2. So when I add them all up together, they beautifully combine into what you will always be able to recognize as the Fkl curve. This is the combination of wave functions that describe all possible emissions and absorptions of those gluons from a dipole. So this structure has the momentum dependence. It's nicely universal. The transverse integral is finite. So I don't have to worry about regulating this super carefully in the infrared or in the UV. It goes to 0 at short distances because of color transparency. It goes to 0 at long distances because the dipole is color neutral. The relevant logarithm, the one that we saw last time, is the one that comes out of this longitudinal integral. This z is the fraction of like front momentum components. So it's exactly like Feynman x. If I integrate this up to the maximum value down to my lower cutoff, I get a logarithm of the energy. And that's exactly what I would have if I had energy independent scattering amplitude. So if I take my initial condition, the calculation we did yesterday, these guys are energy independent, that integral gives me alpha s times a log. So this is the integral form of my evolution equation. This is referred to as the Belitsky hierarchy. This is the full form. And the challenge of this is I started off with one operator, which was the matrix element of a dipole. To solve that evolution equation, I need to know the matrix evolution of a double dipole. Well, I don't know the evolution of a double dipole. I got to go back and recalculate. So I start over. The evolution of a double dipole depends on the evolution of an even more complicated object. So this is not one differential equation. This is infinity differential equations in which 2 parton scattering depends on 3 parton scattering, depends on 4 parton scattering. And if you want to solve this thing, you have to solve everything at the same time. That's really hard. I don't know how to do it. You can write it as a recursion relation in terms of operators. This is Belitsky's hierarchy of increasingly complicated operators. You can also write it in terms of this arcane functional differential representation. This is what's known as the Jim-Walk evolution equation. These two things are formally equivalent to each other. They contain the exact leading logarithmic behavior at small x. But this is not terribly useful for my purposes because I can't solve it and I can't show you where the physics comes from. So let's look at 2 simplifying limits of this general equation. The first limit is the dilute limit. Right? So I have a dipole amplitude, and now I've got something which depends on 2 dipole amplitudes. If I've got lots and lots of gluons in my target, then both dipoles have a chance to scatter. But if my target is dilute, and each of these dipole scattering amplitudes is pretty close to unity, then I could expand, assuming low probability of interaction. So formally what I'm doing is I'm saying, this is my S matrix. 1 minus the S matrix is the T matrix. So I'm saying the scattering probability is small. T matrix is much less than 1. If I make that assumption in the general formula from before and I expand it all out, now I get something much simpler. This is built out of only dipoles. Basically, in this term, I can set this guy to 1 and keep this one, or I can set this guy to 1 and keep that one. This one already has a single dipole limit. That's how I get 3 terms, and thankfully, everybody is made out of dipoles. This is one closed differential equation which you actually have a hope of solving. I won't try to do it here, but you can solve it by Laplace-Mellin transform. Laplace transform was something that I learned in undergrad differential equations, never used again all throughout grad school, and then I had to rapidly relearn how to do it when I started working in this field. When you solve this, you get something quite remarkable. This is giving you the exponential growth as a function of rapidity of gluon density. So if you calculate this, so you solve this evolution equation and you ask, what is the leading behavior at high energy, or the leading behavior as x goes to 0? The solution is your PDF, actually all of your PDFs, doesn't matter if it's the quarks or the gluons, everything is growing at the same rate. They grow as a power law behavior of 1 over x as x goes to 0. When you solve this equation, you do the Laplace transform, you do saddle point expansion. Long story short, you can pull out a particular number in some leading approximation. That particular number is known as the Pomeranian Intercept in the literature. That goes way back to the days before QCD with Reggie trajectories, where people said, whatever power is up here tells me about the effective angular momentum of the particle that we're exchanging. So that's what a Pomeran is, that's where it comes from. We built this out of gluons. This is the perturbative version of the Pomeran, where you can actually calculate it in terms of elementary QCD. So that is BFKL. What does BFKL do for us? Yes, ma'am, question?
Sorry, I think 2 slides back.
Sure.
Which term was the rapidity?
The longitudinal integral here, the dz over z. The z here is the fraction of plus momentum. So it's exactly like Feynman x. Right, so this integral dz over z, z is the fraction. If I had p plus was the original momentum coming in through one of the particles, zp plus is the k plus of the gluon that's coming out. So this dz over z is integral dk plus over k plus, which is integral over the rapidity, where rapidity is 1/2 log k plus over k plus. Okay.
Sorry, Matt.
So this is not the rapidity function.
There are many possible versions of the rapidity. This is the momentum space rapidity. It's not the space-time rapidity, it's not the pseudo-rapidity, but it is the true rapidity of momentum.
Sorry, Matt. We
Yes.
have still 5 minutes for the lecture. That is
Okay.
probably very short. We can expand for 10.
Okay, but there are other lectures after this, and I shouldn't shortchange Douglas. Okay, so this was the main point that I wanted to show you about how the logarithms generate this increasing energy dependence, generate increasing gluon densities. We're essentially in this situation where if you solve the evolution equations in the dilute limit, starting at large x, the prediction is something which is growing exponentially as a function of rapidity y, or equivalently power law as a function of x. That growth cannot continue forever. Eventually, you fill up the proton with so many gluons, so much color charge, that you can't just bram off another gluon and put it wherever you want. Eventually, nonlinear recombination effects become equally important to extra Bremsstrahlung effects. And in that limit, you will turn over this exponential growth and cause a saturation of the density. That's what we're looking for here. This is actually already present in those nonlinear evolution equations. The full terrible version of the Boltzmann hierarchy here is basically unsolvable as written. The other limit that one can take is a mean field approximation. If I could somehow take those angle brackets and split it up to get this matrix element times that matrix element, then I'm happy. It's a nonlinear equation, but it only depends on dipoles and I can still solve it. That's what the large NC limit does for us. I said before that the large NC limit simplifies the color structure. Indeed, it does. It makes the diagrams plainer. It suppresses gluon-mediated correlations between one dipole and another dipole. So you end up with an independent product of two dipole amplitudes. This is now a more complicated equation, but it can actually be solved. This is one differential equation, not infinity differential equations. When you solve this, you find that there is a characteristic momentum scale called the saturation momentum QS. It's essentially a new physical scale coming from the high density. The saturation momentum is proportional to the density of gluons. And that saturation momentum tells you physically the size of the color domains that remain. Basically, you say, I started off with some initial condition down here. Now I added in a billion gluons. And that random walk, it's literally a random walk in color space, in that 8-dimensional color space. That random walk process leads to random color screening. And so at a given value of x, your coherent color domains keep shrinking. And they have a particular size at whatever x you're at. The size of a color domain defines a length scale. 1 over that size is a momentum scale. This is the saturation momentum QS. If you plot the gluon distribution in momentum space, you find that it has a characteristic peak. This is the phase space distribution. There's a characteristic peak around QS, not exactly at QS. It agrees with that same power law tail at high transverse momentum, but saturation regulates the infrared. This is the miracle of it, right? Non-perturbative physics lives down here. Non-perturbative physics happens at lambda QCD. If lambda QCD is here, then I can do perturbation theory, and then when I hit lambda QCD, I give up. But if lambda QCD is here, I can do perturbation theory out there, and the perturbative saturation scale kills the infrared behavior before you hit lambda QCD. So it's a bit of a theoretical idealization, but if I can make the density high enough, then I can make QS a hard momentum scale, greater than 1 GeV. And if that's a perturbative momentum scale, then perturbation theory can tell me everything I need to know about the system. Because I can calculate at high momentum, and perturbation theory itself controls the infrared before you get contaminated by non-perturbative physics. Okay, so a couple of words in closing about why this is so important. This high density of gluons is extremely dangerous for the self-consistency of QCD, because in the linear evolution regime, that dipole amplitude is growing exponentially. That dipole amplitude is an S matrix. It's literally related to a probability. And so what you see is, as I add in more gluons, more gluons, more gluons, my scattering probability goes up. The S matrix of my dipole gets, I guess the T matrix gets closer to 1. The S matrix gets closer to 0. But that linear regime, the exponential regime of BFKL, That blows right past 100% probability and doesn't care. So the linear evolution equations are not tenable. The current experimental situation is not tenable. We have evidence that there is linear leading log evolution. We see the exponential growth. That cannot be the whole story, because if it was, you would shoot right past 100% probability and your quantum field theory is broken. So something that controls that growth and forces you down to 100% probability is mandatory for a well-defined theory like QCD. If you solve the BK evolution equation, you see exactly how that works. It slows down that growth. The growth is exponential in the beginning, and then it slows down. You see that it asymptotically approaches 100%, but it never gets there. This is what I would refer to as the little unitarity problem, right? The BFKL evolution drives you right past 100% probability at a point. Nonlinear evolution, BK, solves the problem of 100% probability at a point, but it doesn't solve the problem of total unitarization of the theory, because even though I might correctly saturate to the black disk at a point, the whole region inside the proton is slowly getting there. So the radius of the black disk is growing as a function of energy too. Even though I guarantee that each point doesn't shoot past 100% probability, the integrated probability might still be growing too fast. That is sensitive to non-perturbative physics. That's something that perturbative QCD can't solve for. But the little unitarity problem is something local in position space. This is something that perturbative QCD can answer. And you must solve this problem. You must solve the small unitarity problem, or else you have no hope of solving the big unitarity problem. So saturation is mandatory. Gluon saturation in some form must exist. Otherwise, QCD is not a unitary theory. It does not satisfy the little unitarity constraint. So the reasons that are usually given for why should I care about small x is, oh, look, I can create an exotic state of nuclear matter. It's like a gluon laser where all the gluons are coherent with each other and they have the maximum intensity allowed by nature. That's all true and that's all really cool. They're also important for initial conditions of heavy ion collisions. If you want to discover the quark-gluon plasma, you've got to disentangle or discover the properties of the quark-gluon plasma. You have to disentangle the final state interactions from the initial state interactions. And two colliding nuclei, which are themselves already at high density, could well be in this saturated regime. So you might need a saturated gluon phase, sometimes called plasma, in your early stages of a heavy ion collision. Yes, all of that's true, but for me, that's not the most important reason. For me, the most important reason is the one that I shared with you yesterday, that this explosion of gluon density is an inevitable consequence of a non-abelian gauge theory. If you have a non-abelian gauge theory, anything which is beautifully asymptotically free, just like QCD, as soon as you have this, you have a non-abelian gauge theory with commutators. As soon as you have commutators, you have a rapidity-independent distribution of soft bosons. As soon as you have soft gluon radiation, which is constant in rapidity, you have large logarithms. So exactly the same feature that makes QCD awesome, UV complete, our best candidate for a grand unified theory of nature, also threatens to blow it up. The same feature that gives you UV completeness here could destroy UV completeness there if saturation doesn't exist. So in my opinion, we need to know whether saturation is there or not. We believe it should be there. We haven't seen it yet. But if it's not there, then QCD is broken irredeemably, right? If we're just wrong and saturation is not there, then QCD does not satisfy a unitarity condition and QCD is not self-consistent. And not just QCD, every non-abelian gauge theory will have this problem. I don't know anything about Technicolor, but I guarantee you Technicolor has a saturation problem. And whatever UV complete theory of nature you're dreaming up, you're gonna have to solve this problem to understand what a UV complete theory really looks like. So the case that I like to make and the note that I wanted to end on is I would advocate that discovering saturation is comparable to the necessity to discover the Higgs boson. The Higgs boson was a mandatory ingredient for the self-consistency of the Standard Model. We believed it was gonna be there. Thankfully, we found it. But maybe the more interesting scenario was, what if there wasn't a Higgs? If there wasn't a Higgs, we'd be back to square one and we'd have to reinvent the Standard Model. The same is true of saturation. This is a necessary ingredient for QCD to be well defined at all. And if it's not there, it's back to the drawing board and not just for QCD. So with that, thank you guys very much. I think you now have, I should say that this point that I like to make about saturation in the Higgs, not everybody agrees with me on this point, but I think you've got enough information to see the arguments that I've laid out, and you can judge for yourself whether you believe this or not. So thank you very much for your attention and your patience as I've rambled on for more than my allotted time. Enjoy the rest of the program.
So, other questions? Yes, Steve. So,
Yes, ma'am.
First of all, thank you. I've really learned a lot from these lectures.
Absolutely.
So I am not sure I really understand the saturation problem. Is one way of stating it that if you go to Lewis X, you get like so many gluons that you risk energy. Gluons for the energy you get in the system? Is that like?
It's not so much an energy conservation problem, although if you're not super careful in how you do your evolution equations, you can run into energy conservation, but that's a theory mistake, not a fundamental aspect of the physics. The issue is just that the more gluons you radiate, the higher probability that you scatter. So as my gluon density increases, I have greater and greater scattering probabilities. And if I just let the gluon density blow up forever, eventually the scattering probability exceeds 100%, and that's not acceptable.
The scattering probability of the electron?
So strictly, it's the scattering probability of the dipole, but the dipole came from the photon. So this would lead to a DIS cross-section that grows too fast with energy. It would lead to a proton-proton cross-section that grows too fast with energy. All QCD cross-sections will scatter hadronically like this at sufficiently high energy. So this is a problem of all high-energy QCD processes. Yes?
How will the EIC help us find gluon saturation?
Ooh, great question. I normally had a slide on this, but I didn't put it in. So back to the EIC comparison. Here we go. Yeah, so this was an important discussion that we had in the negotiations to figure out whether the EIC would be built at JLab or at RIC, because there's a choice there between how high an energy do you need versus the luminosity or other benefits that you might get for other physics programs. And part of the reason for why the EIC eventually went to BNL is because this is the higher energy of the designs. But even so, the highest energy that we can get at the EIC is still lower than the energy at Hera. So part of the argument we had to answer is, if we didn't see saturation at Hera, why the heck do you think you're going to see saturation at the EIC when it has lower energies? And that's fair. The other thing that the EIC has, however, that Hera didn't is ions. And this saturated state doesn't care very much about your initial conditions. If you evolve it long enough, if you evolve it to high enough energies, eventually you reach a state that is independent of your initial condition. Here we go. So for this purpose, I illustrated just like a trivial choice of the initial condition, but I don't lose any sleep over this, because however many partons you start off with, after they radiate 3 or 4 generations of gluons, they start approaching that high density regime all by themselves. So the point is, you can use nuclei to get a head start on saturation. They start off even at lower values of X with higher gluon densities because of their mass number. It's a bit of a back of the envelope formula, but you can say something like your QS squared as a function of X and as a function of mass number scales like A divided by X to the power 1/3. That's highly approximate. The power 1/3 is sort of this saddle point approximation to BK kind of thing. And it's A to the 1/3 mass dependence for the nuclei. But loosely speaking, you can trade off between taking a proton and boosting it an order of magnitude up in energy, which means much more expensive, much more hard to build. Or you could, instead of using a proton, use a heavy nucleus and try to gain a factor there on the density already at your initial conditions. I should also be really clear, though, that realistic estimates for what kind of QS you expect to see at the EIC are not enormously high. Right? If anybody tells you, oh, I'm going to see QS squared of 10 GeV squared at EIC, don't believe it. It's going to be marginal at best at the EIC. We think we can see this starting to get at least greater than about a GeV squared, maybe a couple of GeV squared. Maybe if you put selection cuts on only the ultra-central events, maybe you could push it up a little bit higher. But we're really going to be just pushing into the barest edge of the saturated regime at EIC kinematics, we think. So that's part of why it's going to really take a concerted effort by the community to do a global analysis to find saturation. It's not going to be a smoking gun in a single observable. Yes, sir.
Would glue balls and stuff like that also under like have some sort of point of saturation?
You mean like glue ball scattering?
Yeah, or something.
Yeah,
like
totally.
That existed. How would like what would I guess confine all that?
Do you mean confined in the QCD sense or in the philosophical sense?
In like the QCD sense. Like what would-
Basically, nothing changes about the story. So if I have, I don't know what a glue ball looks like. Maybe a glue ball is this. If I had glue ball scattering at high energies, this guy's going for it, this guy's going for it. The gluons at high S, again, S goes to infinity, T equals constant. The glue balls are going to scatter by gluon exchange. And then as you continue to dial up the energy, the glue balls can also start radiating. It's exactly the same story as you did before. So your initial condition might look different. You might start off with 3 gluons bound together into a glue ball or something. But after you go through a couple of steps of evolution, it's going to start looking like 100 gluons, 1,000 gluons, and it's going to approach saturation in exactly the same way. Does that answer your question, or did I miss the point?
A little bit. I guess it was more along the lines of like what would set the point for that level of like how many gluons can exist in level of saturation.
Okay, it's a little bit of a tricky question because it's not just the number of gluons, it's the number of gluons as a function of momentum. So let me illustrate. Here we go. So what I said before is that in the dilute region, so say down here where the momentum is small, these guys are growing exponentially fast. But in regions where the density is high, this has slowed down. So it's not just that the number of gluons is growing, it's growing differently in different regions of momentum space. So your initial condition will tell you, like, what do I start off with down here? And then in all of those cases, the dilute regions will start to grow exponentially fast and such. So it's not just a question of how many gluons, it's also a question of how they're distributed in momentum space.
Okay, so it would like depend on the like initial momentum.
That's right.
Okay.
But eventually, if you evolve it long enough, there's whatever the structure was down here is going to start turning into this peak, and it's going to start moving out this way. And once that starts to form, you have this universal behavior. You can even write it as a formal attractor for the evolution. Yes, sir.
So what if there are quadruples of the can you still use BK or Jim work is on the
You could probably do 1/NC corrections to BK.
I know that if you do two gluon production.
Yeah, it's not just dipoles. Yeah.
At larger limit quadruples don't
Yeah.
go away.
Yeah, it's only for the like single inclusive observables like this that dipoles are sufficient. Yeah, to do more differential observables, you need more complicated multiple operators. Yeah, absolutely. Yes, sir.
So, like as you said, we do not know whether in PA or AA or even high multiplicity PP that QGP formation does not happen. And then EIC gives us a chance to form even smaller collision systems.
Yes.
But then what probe do we use to find at which system size that QGP is not formed in EIC?
Well, I would go to ultraperipheral collisions right now as my cleanest way of looking at this. But if we still see V2 does not turn off in the smallest hadronic systems that we could get, then I would go to this and I would look at it as a function of Q squared. Ideally, I would expect to see, let's say, V22 as a function of Q squared in DIS. I would expect to see the larger Q squared, the smaller the system. So I would expect to see something like this. And if I still see sizable V2 at this value of Q squared, then I would take a bin with a higher value of Q squared and I would look for where it disappears. So if there is, I don't know, a sudden switch off of the QGP, then I don't know, maybe there's a magic Q squared for the QGP where you have V2 and then suddenly it's 0. I have no idea what that might look like. But if we're looking for a turn off of signatures of the QGP, what I would say is as a function of system size, that would translate to turning off of the signals as a function of Q squared. And you have the ability to go to as high a Q squared as you want at the EIC, whereas you're limited by Proton. the size of the proton or the size of the pion system just by the stable hadrons themselves.
I think we are in time. So I will stop here. I have just a curiosity. Just,
Sure.
So by looking at nature, it could be that neutron star has a color saturation.
Could be.
I mean, no, it's just a curiosity. So do you think that is a possible place where this thing could happen?
Neutron stars aren't really where my mind goes. I would be much more interested in ultra high energy cosmic rays.
Okay.
So if it turns out that the EIC is not low enough X to find gluon saturation, if the LHC is even not low enough X to find gluon saturation, what other choice do we have? Earth is being bombarded by space by ultra high energy cosmic rays, far higher in energy than anything we can produce on Earth. So it's harder. You don't have a hermetic detector for those. But if you need higher energies, that's about the only thing that I can think of.
Okay, I think we can stop here. So thank you again, Matt, for all the lectures.